what about a reaction like this? Carbon reacting with sulfur to form CS2. What's being oxidized? What's being reduced? There's no ions being formed. There's no oxygen. It's not reacting with oxygen, so we can't say, well, it's reacting with oxygen, it's being oxidized. There's no way to tell. So we came up with something called oxidation states to help us figure out questions like this. Oxidation states are just a man-made thing. It's sort of a bookkeeping method for electrons. The general idea is that the electrons in this compound between carbon and sulfur are not shared equally. One of the elements, in this case, I think it would be sulfur, gets a little bit more of the electrons. It doesn't actually make an ion, but it kind of hogs the electrons. And so this is just a method of keeping track of what's going on with the electrons. So we calculate the oxidation state, sometimes called the oxidation number, based on the number of electrons assigned to it in a compound. It's easy, but don't do this. Don't confuse oxidation state with ionic charge. Many times the numbers are the same, and that's what makes it kind of confusing. But an oxidation state is not the same as an ionic charge. In this compound, carbon disulfide, there are no ions, but we can calculate oxidation states to help us identify what's being oxidized and what's being reduced. So here are the rules for assigning oxidation numbers or oxidation states. That looks really messy and complicated, doesn't it? It's actually not that bad. Oxidation states coincide with ionic charges on ions. So if you have an element like copper, does that have an ionic charge? No, it's just copper, no charge. Its oxidation state is 0, just like its charge, which is 0. Here's chlorine, 2 chlorine atoms. Is there any ionic charge there? No, it's a 0 oxidation state. Any element by itself is 0. If you have ions, like calcium ion or chloride ion, where it's a single atom, the oxidation state is the same number as the ionic charge. The ionic charge is 2+, the oxidation state is +2. I'm not going to get hung up on grading your work that you put the plus on the wrong side of the 2. I just want to explain to you why it is this way. +2 is in oxidation state. We put the sign first. 2+ is an ionic charge. This has a 1 - charge. Its oxidation state is -1. The oxidation states of atoms have to add up to the charge on the thing that they're in. So here we have a neutral molecule. The overall charge is 0. The oxidation states of hydrogen and oxygen in this compound have to add up to 0. In a polyatomic ion, overall this has a -1 charge. All of the oxidation states for the nitrogen and the 3 oxygens have to add up to equal the charge. This is a little bit redundant. So in their compounds, group 1 metals form +1 ions, and so they have +1 oxidation states. Group 2 metals form 2+ ions, and they have +2 oxidation states. So all of that corresponds pretty closely to ionic charges. And then the nonmetals, we have to go to another table. So this is a set of rules. And this is how I think of it. So I think of the nonmetals as wanting to have an oxidation state that is equal to the charge they would have if they were an ion. So if fluorine was an ion, what would its charge be? -1. So fluorine would like to have a -1 oxidation state. The group 6A nonmetals all form 2- ions. They would like to have a -2 oxidation state. But they can't, you can't always make everybody happy. Right? So you've got this compound of these nonmetals, and you have to decide who gets what they want. So there's this is the list, the order of priority. If fluorine is there, she gets what she wants first. Then hydrogen, then oxygen, then group 7, group 6, and group 5. So how the heck do you remember that? Anybody like pho? Yummy noodle soup, right? Good stuff. Okay, what if we just erase the end of the P? So this is like pho, right? Except it's a P instead of, it's an F instead of an H. FHO. F, oops, that's the eraser. FHO 765. Could you possibly remember that? I won't give you this table on an exam. No. So, think of noodles. Pho. FHO 765. That's the order of priority. So, fluorine gets first choice, then hydrogen, then oxygen, then somebody in group 7, group 6, group 5. That's how you remember the order. You remember the oxidation state because the oxidation state is the same as the charge it would have if it was an ion. It's not an ion, but that's what it would like to have. Okay, let's do some examples. So here we've got zinc. This is an element. Does it have a charge? No. The oxidation state then is going to be what? 0. Here we have copper 2 ion. This is a monatomic ion. The oxidation state is the same number as its charge. So the oxidation state is +2. Here we have calcium chloride. What are the ions in this compound? We have calcium ion, and we have chloride ion. All of the oxidation states have to add up to 0, but all the ionic charges added up to 0 also, didn't they? So we have 2 monatomic ions here. We have calcium 2+ and chloride -1. The oxidation state is the same as the ionic charge. That's why it's so easy to get them mixed up. So for calcium, the oxidation state is +2, and for chloride, the oxidation state, oh, that's not confusing at all. Let's not use minus signs. Maybe let's use a colon. What's that?
Oh, if they would have been by themselves, it would have been 0.
Yeah, if it was just calcium, then it would be 0. But it's in this compound. This is an ionic compound, and so it does have actual ions, calcium ion, chloride ion. The oxidation states are the same as their charges. CF4. 2 nonmetals. There's no ions, right? So this is where we really need oxidation states, because how do we tell what they are? Well, the oxidation states have to add up to the overall charge, which is 0. But we've got fluorine and we've got carbon, and so who gets first pick? Fluorine. Pho 765. Fluorine's first. What does fluorine want? It wants an oxidation state equal to the charge it would have if it was an ion. If it was an ion, it would be a -1 charge, right? So it's going to have a -1. So then what does carbon?
Even though there's 4 of them?
Even though there's 4 of them, they are each going to be -1. Carbon is going to be whatever is needed so that the oxidation states add up to the overall charge. So what we have here is we have fluorine that has a -1 oxidation state, and we have another fluorine with a -1 oxidation state, and another one, and another one. They're all going to be the same. They're all fluorine. Why would one be different? So there's 4 of those. So altogether, the oxidation state of the 4 of them is -4. We have 1 carbon. The oxidation states have to add up to 0, so carbon must be +4. Is it a +4 ion? No. Is fluorine a -1 ion in this compound? No. This is just how we keep track of what's going on with the electrons. So fluorine's going to be -1, and carbon is going to be +4. Let's look at this one. This is nitrite ion. It has an overall -1 charge. That tells us that the oxidation states of the nitrogen and the 2 oxygens have to add up to -1. So we've got 2 nonmetals, Fe765. There's no fluorine, there's no hydrogen, but there's oxygen. Oxygen gets dibs on whatever charge it wants, whatever oxidation state. It wants the oxidation state it would have if it was an ion, which is what? -2. So oxygen wants to have a -2 oxidation state. So here we have oxygen with a -2 and oxygen with a -2, and there's 1 nitrogen. And so here the combination of those is -4. Let's just separate that off. And this is, we don't know what that is. And those have to add up to -1. So what's the nitrogen going to be? 3. So the nitrogen is +3. Does nitrogen form a +3 ion? No, it doesn't. Is nitrogen happy about having this oxidation state? Probably not. It would prefer to be -3, but oxygen got its choice first. So nitrogen just has to take whatever. Any questions? Yes. Because those are the rules. It has to add up to -1 because the overall charge on this ion is -1. Yeah. Because if we don't have a rule for it has to add up to something, then we can't predict what the charge on nitrogen is. Because these nonmetals can have all different kinds of oxidation states. Sometimes nitrogen's +5. Sometimes it's -3. You just have to follow the rules. The rules kind of seem complicated, but it's actually easier than the other alternative. Question? It adds up to -1 because that's the charge on the ion. So whatever, see this molecule had no charge. So then the oxidation states of the things in it add up to 0. This is a polyatomic ion, and so the oxidation states have to add up to whatever the charge is. Here it happens to be -1. These are an ion altogether, but we can't look at nitrogen and oxygen individually as ions and say what charges they have. Does that make any sense? What about SO3? Does this have a charge? No. There's an ion that looks like this, SO3 2-, but this isn't the ion. This is a molecular compound, sulfur trioxide. So these oxidation states have to add up to what? 0. So we've got 2 nonmetals. I'm going to erase my mess over here. Oops, I didn't mean to do that. I erased too much. 2 nonmetals, so Fe765. Who gets first choice? Oxygen. What does oxygen want? Each oxygen gets -2. You have to look at them separately. There's 3 oxygens. They are each -2. Yes, that adds up to -6. So from the oxygens, we have -6. So we've got 3 oxygens. They are each oxidation state -2. So that adds up. That wasn't a very good 2. Overall, that's -6. And then we have 1 sulfur. In order for these to add up to 0, the oxidation state on all of the sulfur atoms has to be +6. There's only 1 of them. So the sulfur's +6. Any questions? Yeah, that's going to take a little practice, huh? So now, if we go back to this equation that we couldn't identify, we can assign oxidation states and look at what's happening. So what's the oxidation state for C? Element by itself? 0. What about sulfur? Element by itself? 0. Carbon disulfide. So 2 nonmetals, Fe765, no fluorine, no hydrogen, no oxygen, no group 7, but sulfur's in group 6. What does sulfur want? It wants to be -2. So sulfur's going to be -2. That's the same as the charge it would have if it was an ion. And then, so we've got 2 of those, and those have to add with the oxidation state of carbon, add up to 0. So carbon is what? +4. There's 2 sulfurs. They are each -2. Okay? Now we could look at the change in the oxidation state and identify what's being oxidized and what's being reduced. In terms of oxidation states, oxidation is an increase in the oxidation state. Reduction is a decrease in the oxidation state. Reduction is when the oxidation state goes down, is reduced. So reduction is it going down. So 0 to -2, is that the oxidation state going up or down? Negative is down. It's going down. So come on. I was doing the wrong one. That's why you were confused. Carbon is not going from 0 to -2. Carbon is going from 0 to +4. That's going up. So the carbon is being oxidized. And the sulfur is going from 0 to -2. The sulfur is being reduced. Now this is not exactly right, but it might help you remember. So let's just pretend. These aren't charges, but let's pretend they are. If it was going from 0 to +4, would it do that by gaining or losing electrons? Losing. Oxidation is loss of electrons. So this is being oxidized. Reduction is gain of electrons. Sulfur going from 0 to -2. If it was forming an ion, it would be a reduction. Okay? Use oxidation states to identify the element that's being oxidized and the element that's being reduced in this redox reaction. We have to assign oxidation states. Do the easy ones first. What's tin? 0. It's by itself. Let's look at this one. This is an ionic compound. When you have actual ions, the oxidation state is the same as the ionic charge. So SnO2, we've got 2 ions in there, right? Sn and O. What's the charge on an oxide ion? 2-. And tin, in this compound, what's its charge? +4. I'm gonna try to color code this. So oxidation states are going to be in red. So what's the oxidation state of this tin ion? It's the same as the charge, +4. What's the oxidation state of the oxide ions? -2. 2 of these and this add up to 0, just like the charges do. Let's look at this one. So here we have nonmetals. So we have to say Fe765. No fluorine. Hydrogen. What does hydrogen want? +1. What's next? Oxygen. What does oxygen want? -2. Nitrogen has to make up the difference. This is a neutral molecule. All the oxidation states have to add up to 0. So I have 3 oxygens. Each of them is -2. And I have 1 hydrogen is +1. And then I've got nitrogen here in the middle, and there's only 1 of them. So what does nitrogen have to be so all of this adds up to 0? +5. Then over here, NO2. We're not doing anything with the coefficients. That just says how many of the molecule. We're just looking at the formula. NO2, Fe765. Oxygen gets what it wants. It wants -2. There's 2 of those. So what's the nitrogen? +4. H2O, Fe765. Hydrogen gets what it wants, +1. What does oxygen need to be so that all the oxidation states add up to 0? -2. Cool. They both got what they wanted. To see what's being oxidized, we're going to look and see if we can find what is increasing in its oxidation state. Well, what's happening with tin? Tin started at 0 and it went to +4. Is that increasing? Yeah. So this is going up. So from 0 to +4, that's oxidation. What's happening to the hydrogen? +1, +1. Nothing. How about nitrogen? +5 to +4. That went down. That's a reduction. So +5 to +4, that's a reduction. Is anybody else changing? Here's oxygen at -2, oxygen's at -2, oxygen's boring, it's all -2. So tin, SN, is being oxidized. Nitrogen is being reduced. It's not the nitric acid that's being reduced, it's the element nitrogen in the nitric acid. Any questions?